Hi folks, we are on the Unit 1, Day 2, lesson, and this is the first video. Depending on timing, I may break this up into 2 videos, but I think I might be able to get it all in one. So we're going to talk about an introduction to vectors, and for some of you who may have taken physics, you've probably already seen vectors. If you haven't taken physics, that's okay. We are going to go right from the very beginning. And for those of you who have done physics, it's probably only going to be relevant for a couple lessons in this unit and the next unit. Most of our work will be on algebraic vectors, which are pretty completely different and more of a theoretical kind of application of vectors. So just to kind of start off, we're going to talk about what a vector is. So vectors are a way of describing a quantity or a measurement that has both a size and a direction. So for instance, driving 20 kilometers north is a vector quantity because it has a magnitude or a size of 20 and a direction, the north. If you said, I just drove 20 kilometers, that's not a vector because it doesn't have a direction. The acceleration of an object falling due to gravity, that's a really common vector application in physics because the gravity has a direction, it's operating downwards on the object. Another word for size is magnitude, and that's the one that we're really going to use in our discussions about vectors. So we're going to talk about the magnitude of the vector and the direction of the vector. So if we have a definition of what a vector is, then we also kind of have to have a classification for things that are not vectors. And that's going to be called a scalar. So a vector is a quantity having both a magnitude and a direction, and a scalar is the opposite. They're just regular numbers that we've always been dealing with. That's a quantity having a magnitude only. So a scalar could be any real number, and it's any measurement or any measurement of a quantity that doesn't have a direction associated with it. We're going to talk about scalars kind of in terms of real life applications or different science applications of what that might be. But more frequently, we're going to talk about scalars as just the real number system that we are all already familiar with. So it's probably important to take a look at, can you identify which things are vectors or which things are scalars? So the first one, you are 5 years old. That 5 has a quantity, it has a magnitude, but it doesn't have a direction associated with it, so that's a scalar. You're traveling 60 kilometers per hour. So there we do have quantity. We have a size or a magnitude of 60, but we don't have a direction. So that's also a scalar. You're traveling 80 kilometers an hour east. This east, that's the direction associated with our quantity or our magnitude. So that's what makes this one a vector. So just kind of a quick example of what those different quantities, vectors or scalars, would look like in different real life applications. So when we're drawing vectors, we're going to draw it as a directed line segment. And that's a fancy word for an arrow. So it's not a line. As we know, lines have continue infinitely in both directions. And when you're graphing a line in grade 9, I know that your grade 9 teacher harped on you to put arrows on the ends to show that it continued on for forever. That's not the case with a vector. We are going to have an arrow on it, but that arrow does not indicate that it continues forever. It just indicates the direction of the vector, be that the force or the direction of travel or whatever it might be. So it has a beginning, an end, and an arrow on it. So this vector here has a magnitude of 15 because that's my velocity, and it has an arrow saying I'm traveling in this direction. But that the arrowhead is actually at the end of the vector. That's not an indication, like it might be with a line, that that was going to go for forever. And we can always break vectors down into the magnitude or the scalar component and the direction, northeast in this case. So we label the vector with those two components. Whenever we're talking about a direction, we put the direction in those square brackets. That's an indication that whatever is inside there is the direction component of a vector. So that's just a little notation note there. Mathematical notation for vectors. If we have this vector starting at point A, ending at point B, we call A the tail of the vector where it starts, and B is the head of the vector where it ends. We have the direction indicated here, and whenever we're labeling a vector that we're given with a variable name like vector v here, we put an arrow on top. So, and this is always a little bit confusing when I'm switching between platforms. This document was done in Microsoft in PowerPoint, and the Microsoft equation editor puts just this kind of half arrow here. So this is sometimes shown in some textbooks with not a full arrow on top, and some textbooks and also some different equation editors will show a full arrow on top. So this is going to be a difference kind of between textbooks that you might see this year versus maybe if you study this in university. And this is a difference between Microsoft and Google. But these are equivalent notations. Sometimes we show the full arrow on top. Sometimes I think just kind of for ease of kind of faster writing, if you're doing a lot of vector notation, people do that. But either one is fine. Okay. The other notation that you'll see will be if you have a start and end point of your vector, you can label that, instead of labeling it as vector v, we label vector AB. And the order is really important here. This means a vector going from point A to point B in that direction. We always have those arrows pointing left to right. So the arrows are always pointing towards the right. You can label it with the endpoints or with a variable for your vector. You cannot ever draw the arrows on top of a vector variable backwards, going right to left, never. And this is not equivalent. This BA would be a vector going from point B to A. So it would have the same magnitude, but not the same direction. That indicates an opposite direction from our original vector there. So it's not the same if you swap the order of those variables. That's really important. Okay, so the order really matters there. The next thing we're going to look at is a negative vector, and that's kind of what I was talking about there, is a vector with the same magnitude but an opposite direction. So if this vector v means something traveling, say, northeast, the vector negative v, or an opposite vector to v, would be going in the exact opposite direction, so southwest, and have the same magnitude. So that would be vector BA, that would be the negative vector to that. This is an important notation here. These vertical bars indicate the magnitude of a vector. So that's what those up and down bars around a vector variable mean. It means that you're just talking about the magnitude. So vector AB is equal to negative BA. That shows that those vectors are negatives of each other. So if I had AB here, this would be vector BA. So they're the same magnitude but opposite directions. And this notation here shows that their magnitudes are equal. So the magnitude of AB equals the magnitude of BA. So this would be, I could also label that as negative vector V. Okay, so the magnitude signs, that's important notation to make sure you understand. Now, equal vectors, what do we need to have to consider two vectors equal? We need to require both their magnitudes and directions to be the same. So if just the magnitudes are the same but the direction is not, those vectors are not equal. If just the directions are the same but the magnitudes are not, they're not equal. And I want to kind of do a little sidebar and talk about this notation, because this is something that will absolutely come up in later math courses if you continue on to take any math in university. This means if and only if. So this implies causation both directions. And I'll maybe kind of show you what I mean here. So first thing, if I say you're a student in this class and student at res. So if this is kind of an example I use, if you're in this class, that implies that you are a student at Resurrection. If you are a student in this class, you are a student at Resurrection. Does the opposite direction also hold true? If you're a student at Resurrection, are you also a student in this class? Absolutely not. There are lots of kids at this school who are not in this course. So that is not true. But that if and only if tells us that it is true in both directions. So magnitude and direction are equal. So this is kind of just to explain that this is an if and only if situation, and the vectors are equal. This is true in both directions. So if you have two vectors with equal magnitude and equal direction, you know that those are equal vectors. Also, if somebody tells you vector u equals vector v, you know that they must have equal magnitude and equal direction. So this is true in both directions. Okay, so whenever in math notation you see that IFF, it means that the implication is true 100% of the time in both directions. And that's not always the case. A more mathematical example might be if a number is an integer, it is also a real number. So if we had, let's say, x is an integer, that does imply all integers would be real numbers. But that's not true in reverse. If you knew x is a real number, can you say that it's an integer? No, you cannot. So this IFF is a kind of short form of saying this is going to be true in both directions. If one of these is true, then the other is, and if the second one is true, then the first one is true. So back to our equal vectors. Now, notation-wise, we're going to be able to say that the magnitude of V equals the magnitude of W, and also V equals W. So if the direction is the same, the magnitude is the same, then the two vectors are the same. Another notation here, which kind of looks a little similar to that magnitude notation, these two vertical lines between two variables indicate that they're parallel. So if you ever see two vertical lines like that, it means parallel. If you see that, and you guys probably have seen that, that means perpendicular. So just kind of a lot of math notation today, but hopefully that kind of makes sense and clears that up. So can vectors be parallel but not equal? Yes, they can. We could have two vectors that are parallel but not the same magnitudes. So if I had vector u and vector v, those vectors are parallel, they're going in the same direction, but they're not the same magnitude. They're not equal vectors. Can vectors be equal but not parallel? No, they can't. It's a requirement that they have to have the same direction as well as the same magnitude to be equal. We're going to look at two different types of vectors. So the first kind of vectors, and what we're talking about today and for the next couple days, are called geometric vectors. And these are vectors that you would have looked at if you've taken physics. They're vectors in the real world, just out in space or out in the real world, and talking about forces and distance and velocity and things like that. So these tend to be kind of more real life applications, and they're just kind of considered without reference to any sort of coordinate plane. The next type of vectors that we're going to do a little bit toward the end of Unit 1 and then for all of Unit 3 and part of Unit 2 are algebraic vectors. And these are vectors that are placed on the coordinate plane. So we're going to be considering them not as here's a vector that's a velocity of a train, or here's a vector that's a force acting on an object. We're going to look at vectors in a more theoretical form, thinking about how they might work if we define them algebraically and visualize them as directions between points on the plane and then eventually points in 3 dimensions. So algebraic vectors, and we will do a lot more on this later in the unit, are vectors for now in R2. Now R2, that is the normal XY plane that you guys have always dealt with. And we're just going to define it a bit more rigorously. So this is the XY plane that you guys have been plotting points on since like grade 7 or 8, and that you've been graphing on for years. So we can define, and just kind of looking at the set notation here, R2 equals the set of coordinates x and y such that x and y are any real number. So this is just the set of all points on the coordinate plane. And when we talk about vectors on the coordinate plane, we're always going to orient them to start at the origin. Now this is a really important thing, and I'm going to harp on this quite a lot. Vectors have two things. Vectors have magnitude or size and direction, but not location. So any vector will have a magnitude and a direction, but it doesn't have an associated location. Vectors are equivalent no matter where you move them. So we can just kind of reorient, and that's what we do in algebraic vectors, is reorienting everything to start at the origin. So it has a magnitude and a direction associated with it, but it doesn't necessarily have a location. This vector here with the same magnitude and the same direction. I've drawn that pretty close to equal, I think. But this vector could be drawn up here, and it's actually the same vector. So we don't have a location associated with it. Just kind of for ease of use in algebraic vectors, we always kind of default and reorient these to start at the origin, because then we can define them with a point. And it's the point where the vector would end when it starts at the origin. And we would have a negative vector as well, and represent that by the vector with the same magnitude and going in the opposite direction. Okay. We're going to have the same kind of notation for magnitude with algebraic vectors. We would still have opposite vectors and equal vectors. And the notation is really pretty much the same. Just we will have that way of defining it with where it ends up if it starts at the origin. So we're going to take a look at this rectangle, and let's see if we can find two vectors with equal magnitude. And you probably can. A lot of vectors are going to have equal magnitude. What I want you to focus on is the notation here. So the magnitude, maybe the first one I see is BC and DA. So the magnitude of BC equals the magnitude of DA. Okay. I also could look at different directions. I could look at these sides. I could look at diagonal vectors, which I think I might do. And I believe in your note it specifies equal magnitude but not equal or opposite direction. So what about vector AC and BD? This is a rectangle, so their diagonals are equal. So there's a lot of different possibilities. So AC and BD.